Okay. Okay. Stephanie, let me give you your homework back right away here.
Okay. My phone's getting better every time, but mine's done. I don't see anything.
Okay, let's go ahead and get started. Good to see all of you guys. My voice is quite a bit better, but I did forget to bring anything to drink today, so we'll see how I do. I might need that. We'll see. Hopefully you guys are handling the weather all right and the studying. Let me go over a few just basic general things. First of all, tomorrow is our final at 5 o'clock, and I have not written it yet, so that's Wednesday, and it's in our usual classroom. So upstairs in our usual room at 5 o'clock. If we can get everybody there 5 or 10 minutes early, we'll just start a little early. So try to be there on time or early. Let's see. If you would like to do the proof section of the exam, which is about 20% of the final, outside of this time block, you may do that. The hardest part of that is you're just going to have to catch me. I will probably be in by 10, and I'm planning to try to stay in the whole day. In fact, I'm hoping to actually bring in lunch so I don't have to even go out for lunch tomorrow. If for some reason it doesn't work because you have other finals or whatever, you could even ask me, you could even do it after the final's over tomorrow evening if that's better for you. So just keep that in mind that you don't have to do the 2 proofs during class, and I would advise you not to, so that you can have even more time to work on the rest of the test. Christine?
Continue on.
Yeah, Allison?
Wait, so are we going to get the proofs tomorrow at 5 o'clock with the rest of the final then? Then we just
What I'll do is if you take the if you take the proofs outside of the regular class time, then when you get the final, you just ignore that page because it will be the same page again. Anybody who's taking it during class will be doing the same proofs, but if you come in and want to do it outside of class time, I'm going to pick the 2 problems that you're going to do on the spot.
Yeah.
So let me just, so everybody's going to get different. So you don't need to ask your friend, well, which 2 proofs or which, I think what it is there's 5 proofs there, right?
Yeah.
And I said 4 of them are going to appear, and you're supposed to choose 2 out of 4, right? So so basically 1 of the 5 will not appear on the exam. If you do the proofs outside of the regular time, which of the 5 doesn't appear will be randomly decided on the spot. So it might be different for different people. Does that make sense? So it doesn't help to go ask your friend which 4 proofs showed up on your test because they may not be the same. But the other thing is, if the way you're going to do that is you're going to come to my office.
Yeah.
And you might have to hang out, wait for me a little bit, but I will take you to a quiet place to do this. I'm not going to have you just do it outside with all those crazy people out there. We'll go to, I have secret little rooms that are very quiet. I'll sit you down and you can just write up your proofs and take as much time as you need to write those up, although it shouldn't take that long.
How will we be in your office tomorrow?
Well, I said I'm going to get in around 10. I'll basically try and be there most of the day until before the final starts.
Sorry, you said if we go before you choose the 2 that we do, or you just give us the 4
No,
options?
no, I'll give you the 4 options. You're gonna. I'm sorry, I said
That's
that.
what it sounded like too. Yeah.
I'm sorry. The same rules
Same rule.
as what the people who might take it during the final will have, which is you will have 4 proofs printed there, and you're going to choose 2 of those. Yes.
If we choose to do it outside of the final time, would we not be able to work on it during the final time?
Right. Yeah, because I don't want you starting to work on it outside of final time and then go figure out everything you need to fix and then do it. You have to have it right. You have to only do it when you're ready to do it. Christine?
I have a couple questions. So if we show up as like, let's say 2 residents people show up in your office at the same time, are we going to be sitting in the same?
No, I'll find a separate places.
And then let's say we like blank on it and we know, let's say like parts of all 4 of them, or we know parts of some of them. Can we get like partial credit?
I will only grade the 2. I will only grade 2. You have to choose 2. Make sure you know the proofs. And I will be grading those very strictly, by the way. I will grade those proofs the strictest of anything I've graded all semester. Make sure they are absolutely correct, because you have the notes, you know exactly how they're supposed to read. So you have to choose the two proofs, and you have to make sure they're correct. I will take off points if they're not. Yeah.
So your grading strictly, is it like compared to what we did in class, or do we need to fill in like all the details that you skipped?
I hope I didn't skip too many details. If I skipped some details, you could skip those details. Yeah, but I don't think I skipped very many.
Not very many.
Okay.
You just need to know it verbatim, right? Like we put stuff into our own words as long as it's correct.
Yeah, this isn't about regurgitating exactly what I wrote down. This is about providing a correct proof of 2 out of the 4 out of the 5 statements. But you'll have 4 statements there and choose 2 of them to work on. Does this make sense?
Yeah.
Okay. All right. Any other questions about that part of it, the proof part of it? If a bunch of people show up all at once, I will run everybody in different directions and find a quiet place for all of you to work on. And we just what I'll probably ask you to do is just leave your stuff in my office while you're doing that, except for your pencil. So that way you have a nice storage facility. That's why I have a nice big office. So okay, everybody good on that? Any questions on any of that? Okay, great. There's that one. Okay, so that's about the proofs, and then the rest of the final, of course, you know, hopefully you've been looking at the review packet. It summarizes a lot of the important topics that we went over. Yeah, so Trenton, for example, I say here that I do expect you to know what the Gram-Schmidt process is, but I won't be asking you calculations based on it. So that would be in section 6.2. Right, so don't worry too much about that. So just go through this list of topics and make sure you know all the words, and it might help guide you to compare it with your class notes. Make sure it's all lined up well. Let's see. I think that's everything you need to say about that. There's a sample final up. If you haven't done that yet, you might want to try that tonight after the review, see how it goes, check the solutions, and so on and so forth. Then you can ask me questions if there's anything that's not clear from that. Okay, so this is not the right sheet. Here we go. I want to talk for a little bit, I've got some sample problems here. I actually want to do a couple of problems that aren't in the review packet first, because there were some issues with this homework assignment that I just passed back. I thought maybe we need a little bit more effort on 6.3. So I'm going to give that to you. So let's call this final exam practice. The main thing we're going to do here is a lot of practice problems. By the way, you should expect fairly even distribution of the topics with a little bit of emphasis on the Chapter 6 material and the Cayley-Hamilton section, which is 5.4. So 5.4 along with 6.1 and 6.3, those are the sections we've done since we had a midterm. Okay? So here's the first one I want to work out with you. So let U and T both be linear transformations from V to V. What I'd like to have us try and do is prove that the adjoint of U composed with T is the same thing as the adjoint of T composed with the adjoint of U. Notice that the order of the two linear transformations switches. If you think about it from the matrix perspective, you say, yeah, that makes sense because the adjoint is like the conjugate transpose. And we should have learned in 250B that when you transpose a product of matrices, you end up taking the transposes of the individual matrices, but in the opposite order, right? So it's not surprising that this is true, but I saw a lot of people on the homework, I think you were showing that if T is invertible, then T star is invertible. And so to show that T star is invertible, you have to do some calculation like this. I saw a lot of people not switch the order of the T and the T inverse when they combine these together. So that was the reason it prompted me to put this one on here to practice with. Okay? So there are actually two good proofs of this statement. I'd like to present both of them to you. One of them avoids matrices altogether and just uses the definition of the adjoint operator. And then the other one is where we do use the matrices to sort of say, well, we can turn questions about linear transformations into questions about matrices and then go back again. So I'd like to show it to you both ways. So there's going to be two solutions here. And by the way, this is actually in the book. It's a theorem 6.11, I believe, in the book. So I didn't cover it in class, but it's perfectly fine to actually go ahead and prove it here now. So the first solution is to kind of use the definition. Let's just recall the definition of T star. So T star is defined as the unique linear transformation from V to V with the inner product of T of x with y equal to the inner product of x with T star of y for all x and y in the vector space, in the inner product space V. So that's just the definition. So, does this make sense? The definition of T star is that it satisfies this equation for all x and y. So therefore we kind of know the definition of the left-hand side. The definition of UT quantity star is just that the inner product of UT, okay, so we have, let's just look at it, we have UT of x with y, right? The definition of UT star is that I can take UT, put it on the other side with a star on it, right? What I'm going to show you, though, is that T star U star gets you to that same point. And since there's only one of those functions, since there's a unique transformation that allows you to move the UT to the other side, then if I can show that T star U star does that, well then it must be this guy. Because this guy is the unique transformation that satisfies this equation, basically. Okay? So, for instance, when I'm looking at this right here, I can actually kind of view this as, okay, let me just emphasize here. It's U of T of x. When we have a composition, that's how we actually mean it. So what we actually have here is we have U of something inner product with y. So take a look up here. If I had U of something inner product with y, I could move it to the other side as a U star of y. So let's actually do that. Whatever this, so this x right now is starring in the role of T of x. So I'm going to leave the T of x there, and I'm going to move the U to the other side, but I have to put a star on it when I do that. Everybody follow that? And now do you see what I'm going to do next? What am I going to do next? Do it with T. Do the same thing with T. I'm going to move the T across, so that's going to leave x by itself in the first entry, and it's now T star of U star of y. Okay? So there you go. This guy right here is T star U star of y. So we have moved the UT to the other side using T star U star. So therefore T star U star must be this thing, because this is the unique thing that accomplishes that. Okay. So UT star is equal to T star U star. Everybody all right with that? Okay. So that's one way to solve the problem. That's one very nice way. You could do the same thing with U plus T. You could do the same thing with a constant times T. right? So there's similar, so you might want to look at this theorem 6.11, there's some other parts. Since I showed you one of them here, then I think you probably could try the other parts and handle those. Or maybe I'll just ask you to do it tomorrow, I don't know. Be something worth trying. Everybody all right with that? Okay, I'm going to give you another solution. I'm going to give you a different solution. Solution number 2 to the same problem. This one is going to show it to you using matrices. So we do know that we can take any transformation and write down a matrix representation with respect to a basis. So if I choose a basis and I show that the matrix representation of this transformation relative to that basis is the same as the matrix representation of this transformation with respect to the same basis. So if two transformations have the same matrix representation with respect to the same basis, then they are actually equal, right? In other words, what I'm saying is, T1 equals T2 if and only if, for all basis beta, T1 relative to beta is the same as T2 relative to beta. Actually, it doesn't even really need to be for all. I could just as well say there exists a basis for which this is true. Okay. It's equivalent to that. Okay. So far so good? So what I'm going to do to show that these two transformations are equal is I'm going to look at their matrix representations relative to some basis. Does anybody have a suggestion? Is there anything about that basis that we might want to impose here? An orthonormal basis would be a great idea, because we have a theorem that says that the matrix representation of the adjoint of something with respect to a basis is the conjugate transpose of the original transformation. But that's only if you use an orthonormal basis. So what I'm going to do here is I'm going to let beta be an orthonormal basis for V. Right? So then what I want to do is I would like to look at UT star with respect to beta. I'm going to look at that matrix representation right there. What I know, and the reason that I chose an orthonormal basis, is because theorem 6.10 tells me that as long as I use an orthonormal basis, the matrix representation of the adjoint of something is really just the matrix representation of the original transformation, but with a conjugate transpose on it. Make sense so far? Now, I have UT, the composition of U and T with respect to beta. First, I do that first, then I conjugate, then I... Actually, conjugation and transposing are commutable. It doesn't matter which one you do first or second. But in this context, I'm first calculating the matrix of UT with respect to beta, and then doing those other things. So can anybody help me out below the bar here? Below this bar, do we have anything that we can do with the matrix representation of UT with respect to beta?
We can change it to U with respect to beta and T with respect to beta?
Absolutely right, okay? U with respect to beta times T with respect to beta. We're still putting a bar, we're still transposing. That's by theorem 2.11. That goes way back to theorem 2.11. Okay? So we have that. We have that so far. Okay. So, knee-jerk reaction here. What would you maybe tell me to do? I split the two matrices up. That's good. Pardon?
We can distribute the transpose.
Okay, distribute the transpose. What happens when you distribute a transpose? They switch, don't they? And actually, you can also distribute the conjugation bar. Right? So this actually becomes T sub beta conjugate transpose times U sub beta conjugate transpose. Okay, are we all right with that? So that's just properties of transpose from Math 250B. Properties of transpose in 250B. Okay, everybody make sense of that so far? All right, so now, we got the T and the U switched around. That's a good thing. So now what would you tell me? Say again? This one, right, exactly. This is the conjugate transpose of just T. So this is just T star, right? Well, it's T star with respect to beta, right? And then this one is just U star with respect to beta. And then I can use my theorem 2.10 again. That's a nice problem. Use my theorem, I'm sorry, 2.11. I use my theorem 2.11 again to put it back together into a single thing. So T star times U star relative to beta. So look where we started and look where we're at now, right? We have matrix representation of UT star. Over here we have matrix representation of T star U star. Therefore, they're the same transformation. Okay? So UT star is equal to T star U star. I like it. So I think and this step right here is the only one I didn't explain. This one would be theorem 6.10 as well. Please be sure to tell me, if I give you a problem, anything like this, be sure that you tell me that you're working with an orthonormal basis. You guys all got that right on the homework. There's a true-false item about whether the T star is the same as the conjugate transpose of T. And you all got it right that was a false statement because they didn't put in that it was an orthonormal basis. You have to have an orthonormal basis for that. Yeah?
Do you have to memorize the exact numbers for all of them?
No, you don't have to know the numbers of the theorems. I'm just putting them in here because I happen to know them, and that way you can refer to it, look back at stuff.
If we were to refer, can we just say like a theorem?
Just by theorem from class.
Okay. Ooh,
Just make sure it was a theorem from class.
Yeah,
I think I was there every single class, so I don't think I missed anything. So I will know if it wasn't actually there. Okay, everybody all right with that? Let's try another example. How many of you have looked at that group work 8 that I? Okay, maybe you haven't done that. So then let's maybe do 2 examples here. I wanted to do one that isn't just group work 8. If you haven't looked at that problem on group work 8 that I didn't give you enough time to do, you really should look at that. It'll be very helpful. But I'm going to show you another example right now, and you'll see how complicated these problems can start out looking very simple and get pretty complicated. Okay, Shamram knows. Okay, so here we go. Let's take V to be R cubed. This is kind of computational though, so in that sense, should be happy. So let's define. Yeah.
This was from 6.3.
Yeah, I'm still on 6.3. I'm focusing a lot on this section because I just wasn't totally happy right at the end. I felt like maybe I didn't do quite enough on this, so I just want to make absolutely sure. I'm going to define an inner product. Let's say we took ABC and XYZ, and I'm going to define it. Okay, now here's the first wrinkle. I'm not going to give you the standard inner product. The normal dot product would just be A times X plus B times Y plus C times Z. I'm going to give you 3AX plus BY plus 2CZ. Actually, one thing I could ask you right now would be to verify, if we wanted to do a part A, verify that that is a valid inner product. Do you guys know the 4 axioms? No? These should be on your flashcards under your, well, because you only have one more night, under your pillow, one more night, the 4 axioms of an inner product. So, should we do that?
Yes.
Yeah. Okay, I'm going to call that part A. Okay, so this first part is actually not 6.3, this is 6.1, verifying the inner product axiom. So verify this is a valid inner product. Actually, here's a little theorem for you. Anytime you have Rn and you do something like this, you can take the regular standard dot product and put any scalars in front that you want as long as they are positive. As long as you choose positive scalars, it will be a valid inner product. The minute you put a scalar in front that is 0 or negative in any one of those terms, it will no longer be a valid inner product. So that's kind of an if and only if statement. This will be a valid inner product provided all of the scalars in front of each of those normal looking dot product terms are positive. Okay, so I get confused because I teach 250B and 307 and the order in which the axioms are listed I think is different.
Yeah.
So what is the first axiom that you guys want me to check?
Closure under addition.
Second? Okay, that's the fourth axiom. It's the first axiom in my book, but it's the fourth axiom in the 307 book. What's the first axiom?
It's the closure under addition.
It's the addition one?
Yeah.
Okay, which is the one that's usually the most painful anyway. So let's just say we take A, B, C, and we're going to add it to A prime, B prime, C prime, and then inner product that with X, Y, Z. Is this the right thing?
Yes.
I'm thinking of the right one? Okay. So what's the first step that I would need to do right here? Add these two together, right? Okay, good. So this is, so I'm only working on the first slot, so I have the point A plus A prime, B plus B prime, C plus C prime. And I'm taking the inner product of that with X, Y, Z. And that now, that can be calculated using the formula. So it's 3 times the first slot, which is A plus A prime, times X, plus the second slot, B plus B prime times Y, plus the third slot, 2 times the third slot, C plus C prime times Z. Right? And then what would you want me to do here?
Distribute the X, Y, and Z.
Okay, I can multiply it all the way out, and then let's kind of move ahead here because we're going to
And
get...
put all the prime terms together and put all the non-prime.
Okay, so we'll try and put all of the prime stuff together and all the non-prime stuff together. I'm going to break this into 2 pieces here. Okay, so I'll have, what will I want to put here at the beginning? 3AX, and then B and Y, and 2CZ, right? Okay, and then on the second term, it's the same thing except 3A prime X plus B prime Y plus 2C prime Z, like that. Okay, and the reason for doing that is now your first entry is just the original inner product. So it's just ABC with XYZ, and then plus the second part is just the inner product of A prime, B prime, C prime with XYZ. Okay, so that would do it. That look okay? Okay. All right. What's the second axiom? Scalar multiplication one. So we have I need a constant. Let's call it K. So let's let K be a constant, and it would be a real number if we're in a real inner product space. So we're going to take the inner product of K with ABC, comma, XYZ. So I'm going to squeeze this into the space I have here. What's the first thing I would do? Right, distribute the K through. So I would just get inner product of KA, KB, KC with X, Y, Z. And now I have a single vector, inner product with a single vector, so I can just use the formula up there. All right, so I'll have 3 times KA times X, and then plus KB, Y, plus 2KCZ. Looks good to me. Yeah, you look at that and kind of a no-brainer. You want to pull the K out. So it's K times 3AX plus BY plus 2CZ. And that's just K times the inner product of ABC with XY.